Hi there. So while this video focuses on inverse functions, it is setting the stage for this entire unit, which will be eventually getting us to working with logarithmic functions and exponential functions. Okay. At the top here, to determine if a relation is a function, we use what's known as the vertical line test to make sure that for every y, there's only one x, or in other words, that all of your x values are different. Fact just below that, a function is one-to-one. That's how this is read, is a function is one-to-one when it and its inverse are both functions. And inverses are simply found by switching your x and y coordinates. So in the example below, in the left-hand column I have years, in the right-hand column I have the stamp price. It's asking us, is this an example of a function? If all of the x values are different, it's a function. So we go down and look at my years. Every single one of these years are different. So yes, this is a function. Okay. And I'll write here yes because all x values are different. And then if we move over to the example on the right, they say, well, let's find the inverse and determine if it's a function. As I just said a bit above here, inverses are found by just simply switching your x and y coordinates. So that means the stamp prices will go here on the left, and they'll become your new x's, and your years will become your new y's. So 0.15, and then I have 0.20, 0.20, 33 cents. These are all money, so 37 cents and 44 cents. And then put in my years, so 1978. I'm just going to do it like this, 83, 84, 99, 2004, and 2010. Okay, so now we ask, is this a function? Are all of your x values different? And hopefully you would agree. Nope, we got a problem here that in 1983 and 1984, you've got this stamp price of 20 cents that repeats itself. So we would say no, because x value of 20 cents repeats itself. The example below, they ask us, all right, just these two ordered pairs here, is this a function? Are your x values different? Yes, if they are, then it's a function. Is the inverse a function? So you notice here all that I did between these two ordered pairs is just switch them. Ask yourself again, are the x values different? I got a positive 7 and a positive 0. Well, 0 is really positive or negative, but those are both different, so yes, it's also a function. Just below that, a couple of facts. We use the vertical line test to determine if f of x is a function. We use the horizontal line test to determine if f inverse of x is a function. Vertical line test is if you draw a vertical line and you only pass through one point on the graph, then you pass the vertical line test. Horizontal line test is drawing a horizontal line through your graph. And if it only passes your graph at one point, then it passes the horizontal line test. So, if your function passes both the vertical line test and the horizontal line test, then your function is known to be one-to-one. So down here below, they have given us a sketch of a function, f of x, and they want us to sketch the graph of f inverse of x. So what I did is I identified down here 3 major points that we can all agree are definite points on this graph. So we're saying this blue curve here, this is f of x. And so I identified these 3 major points here that are on the graph of f of x. Well, if we then want to find the points on f inverse of x, then that would just be switching the x and y coordinates. So I'll get a different color here and say that, okay, well, the point -2, -4 is going to become -4, -2. 0, 0, when you swap them, you still have the same thing. And that last order pair, 2, 4, is going to become 4, 2. Now, if we plot these points, -4, -2, 0, 0, and then +4, +2. I'm going to try to do this as best I can here. I want to try to something like that. Kind of should have gone up a little bit more like there. A bit better. Okay, that would be the graph. Okay. This one should kind of come out a little bit more straight than I had it. I think that's the way I want it to look. All right, so moving on from here, you can there's a fact just below here. It says a note: all inverses are reflections across the line y equals x, and the line y equals x is here in the center, And then, because that's your origin, is 0, 0, that's the y-intercept at 0, 0, and then your slope is up 1 over 1, up 1 over 1. Now I'm going up 2 over 2, but that's the same thing, because 2 over 2 is still going to give you 1 over 1. And if I try to draw a dashed line there, it's not perfect, but it's fairly decent here, that if you were to reflect over that dashed line, the red line would be on the blue and the blue would be on the red. Okay, like I said, it's not perfect, but that's what it should look like. Okay. Um, just below that, they say they want us to use the horizontal line test to determine if your function is one-to-one. So here in example 2, we'll look at this one together. In example 2, they want us to graph y equals 3 minus x. So we know we have a y-intercept up here at positive 3, and then my slope is down 1 over 1, down 1 over 1. And then I just connect my points here. I know that this is a function because it passes the vertical line test. Anytime I draw a vertical line, I only pass through one point. I know that it will be that its inverse will be a function because anytime I draw a horizontal line, and I'm going back to that original black line there, I'm only crossing my graph at one point. Okay, so it passes vertical line test. It passes horizontal line test, so therefore my function is one-to-one. So I'll just say here y is one-to-one. Okay, so that's the idea, is that you are drawing vertical lines to see if your function passes the vertical line test, and then you're drawing horizontal lines to see if your function passes horizontal line test, and if it does, then your function is one-to-one. It has to pass both of those tests. And vertical line test, again, is that you draw vertical lines and that each time your graph only passes through one point on your graph. And then horizontal line test, you repeat the same thing. You draw horizontal lines, and if your graph, you only cross your graph at one point each time, then you are passing the horizontal line test. Okay. I'll go ahead and do example 3 here together with you so you can kind of see what the difference between the two. If you were to graph this in your calculator, you'd find that it looks something like this. Now, we can see that it's a function because it would pass the vertical line test, and I hate to keep drawing these lines because I feel like that's distracting, but if you draw a vertical line, your graph is only going to pass through one point, so vertical line test, it passes. Horizontal line test, though, this time, look what happens if I were to draw a horizontal line. If I were to draw a horizontal line through there, it would pass. But you can't just, draw one horizontal line. You've got to look at the entire graph. And if I come up here and say drew my horizontal line there, I cross this graph 1, 2, 3 times. So if you ever cross your graph more than one time, then you fail that test. So I failed the horizontal line test. So we can say here that y, my function, is not one-to-one. Okay. All right, I'm going to flip it on over. Top of the next page gives us a formula for finding the inverse if you're given an equation of a function. Like, how do you find the formula for the inverse? It's a very straightforward process. All that you do are you switch x and y, solve for y, and then after you've solved for y again, you replace your y with f inverse of x. And that f raised to the negative 1 power, that's the notation for f inverse of x. Fact down here just below that is that the domain and range of the inverse is just the reverse of the domain and range of your function. In other words, the domain of your function will be equal to the range of the inverse, and the range of your function will be equal to the domain of your inverse. I'll illustrate that for you down here below in example 4. I'm actually going to do example 4 with you. I'll let you try example 5 and 6 because they're a lot easier. But I'll do example 4 here with you. If I show you the harder one, that should be good for you. And then you've got the solution key to check yourself by. Okay, so let's look at example 4 here. And they first ask us to determine if this is one-to-one. So in order to determine if it's one-to-one, you want to take a moment, put it in your calculator, get a rough sketch for yourself. You should see that you have a vertical asymptote there at negative 1/2. We've got a horizontal asymptote at 5/2, which is 2.5. So that's just bringing back in information from a previous unit, right? That you find your vertical asymptote by setting the denominator equal to 0. Find your horizontal asymptote by looking at your degree. So take 5 over 2, and that's 2.5. So there's your horizontal asymptote. And you could, of course, you could put this in your calculator, but I just thought this would be a nice way to revisit what we were doing before. Now graph this function. So if I graph this function, you would find that graph looks something like this over here, and like so. It's not perfect, it's just nice, like I said, a nice rough sketch. Now to determine if it's 1-to-1, ask yourself, does it pass the vertical line test? Hopefully you agree. Yes, it does. Does it pass the horizontal line test? Yes, it does, right? Anytime you draw a vertical line, you only pass through one point on the graph. Anytime you draw a horizontal line, you only pass through one point on the graph. So this function is 1-to-1. So it passes both. So y is 1-to-1. Step 2, let's find the inverse. So to find your inverse, I'm going to write out my function here. Y equals 5x minus 3 over 2x plus 1. The steps above said switch x and y. So everywhere you see a y, you plug in x, and everywhere you see an x, plug in y. And now my goal is to solve for y again. So you can think of this as like x over 1, and we can just cross multiply. So x times 2y plus 1 equals 1 times 5y minus 3. I'll just burn an extra step here. Now let's take this x and distribute it through. So 2xy plus x equals 5y minus 3. Now from here, your end goal is to solve for y again, so that hopefully the next logical thing then would be is that I need to get my y's all together. So I'm going to take this 5y to the other side, subtract 5y. So now that leaves me with 2xy minus 5y plus x equals -3. Next step, I want to get closer and closer to getting these y's all by itself, so I'm going to pull my x to the other side, so I'm going to subtract x. And if you want to do all that at one time, you certainly could. I just like to show all my work here. Minus 5y equals -x minus 3, or if you write -3 minus x, that's the same thing. Next step, you want to solve for y. You notice over here on the left-hand side, you have two terms, and they both have a y in common. Factor that y out, and write what you have left over, and that would be 2x minus 5. Now to get y all by itself, divide by 2x minus 5. That way you cancel out, and so now you've arrived at y equals -x minus 3 over -2x minus 5. I've really come down here in this other spot, haven't I? So now the last step was you replace that y with f inverse of x. So f inverse of x is equal to -x minus 3 over -2x minus 5. You have found the equation of your inverse at that point, okay? Now, step 3 wanted us to find the domain and range. So step 3. Let's look at f of x first. F of x, that's the original function, that's your graph back over here. If you look at the domain of that function, well, you remember it had a denominator in it, and so that had a vertical asymptote, and so we were able to see, oh, okay, well, my domain then, where's the purple parts being graphed? From -infinity to -1/2. Remember that -1/2 came from setting the denominator equal to 0 and solving for x. So you'd have 2x equals -1, and then x equals a -1/2. That would be your vertical asymptote. So my domain then is running from -infinity to -1/2, and then picks back up and goes from -1/2 to +infinity, because that's the right-hand side of the graph here. Okay, let's look at the range of that function that we have graphed here. So the range of my function here, reading it from the bottom to top. So my range of this bottom portion here is coming in from -infinity up until this y value here. That corresponds to your horizontal asymptote, which was the line y equals 5 over 2, right? That's your horizontal, since the degrees were the same on the top and bottom, we just took the coefficients in front. So my range is coming in from negative infinity to 5 halves, and then it picks back up on the other side of 5 halves and goes to positive infinity. So then 5 halves to infinity. Now, if we look at f inverse of x, then think about its domain and range. For the domain here, look what would happen if you remember the domain we find by setting our denominator equal to 0. So if you set negative 2x minus 5 equal to 0 and solve for x, you're going to add that 5 over and you get negative 2x equals 5. And then sure enough, you're going to divide by negative 2. And I'm going to have, I just caught a mistake. Over here, back, let me draw your attention. Back down here, when I divided by 2x minus 5, I wrote it correctly here, but when I rewrote it down here, I put a negative, and that does not need to be, that 2x is positive. So let me erase that. Come up here and let me erase that, because that was causing a problem. I was thinking there's something wrong. All right, so now I set 2x minus 5 equal to 0, add that 5 over, divide by a positive 2, those are positive 2's, and then I get x equals 5 halves. That's your vertical asymptote for the inverse function. So that's your vertical asymptote here for this inverse function. So we can say then my domain then is going to be from negative infinity to 5 halves, union 5 halves to infinity. Like we did back in the very first unit, okay? Then think about your range. Your range was associated with your horizontal asymptote. Look and see what your horizontal asymptote here would be. Take the coefficients, as the degree is the same on top and bottom, and you have negative 1 over 2. So sure enough, here my range then is going to go from negative infinity to negative 1/2, and then negative 1/2 to infinity. Now, I purposely talked you through finding the domain and range here of both of these pieces. You would need to find the domain and range of your original function, but when it comes to finding the domain and range of your inverse, that fact that I had just above here, notice how the domain of your original function is the same as the range of the inverse. And the range of your original function is the same as the domain of your inverse. So they just switch with one another, okay? So sorry about that mistake. I'm sure you were probably, if you were following along, thinking, well, where'd she get that negative from? Glad I caught it, okay? All right, so I'm going to let you pause the video and try example 5 and 6 and check yourself with the solution key. I'm going to scoot on over and do the problem at the top of the next page, which is very similar to that one. It's just talking about a domain restriction. So here on example 7, they say, well, given the graph of y equals x squared, they want to know if it would pass the vertical and horizontal line test. So we could crank out that graph for ourselves. Here's the graph of y equals x squared. It would definitely pass the vertical line test. Anytime I drew a vertical line, it would always pass. But horizontal line test, it would fail, right? I would pass through more than one point. So it passes the vertical line test, but fails horizontal line test. So just below that, you see here, well, since it won't pass the horizontal line test, we can just restrict the domain to be x values greater than or equal to 0. So if you're restricting to x values greater than or equal to 0, you're just looking at this portion here that I've highlighted in green, just looking at that portion. And if you look at that portion only, okay, so you're ignoring this over here, I'm just looking at y equals x squared, but only for x values greater than or equal to 0, then I'm just looking at that portion there, and sure enough, that would pass horizontal and vertical line tests. So with that said, they want us to find the inverse of y equals x squared with our restricted domain. So our rule, switch x and y. So x equals y squared. Solve for y again, so to get y all by itself, take the square root. So the square root of y squared would just be y. And then you would get here y equals the square root of x. Now technically when you take the square root you have plus or minus, but we were only looking at the positive side, so it will only be the square root of x. Replace that y with f inverse of x, And so f inverse of x is equal to the square root of x. So there's your inverse. I think it's probably worthwhile to look at again the domain and range. So let's look at domain and range of f of x. Okay, so domain and range of f of x. For my x values, I'd restricted that for you. So you had to go from 0 to infinity. And you could equal 0, so I'd put a bracket on that. The range would actually end up being the same thing, right? You start at 0 and you go up forever. So that would also go from 0 to infinity. Oops. Now, f inverse of x, if we just go off of what our fact on the previous page said, then the domain and range is just going to be swapped. So if the domain up here is from 0 to infinity, then that means the range down here is 0 to infinity. And if the range up here for the function is 0 to infinity, then that means the domain is 0 to infinity. And sure enough, if you were to graph this, the square root of x, that's your inverse function, it looks like this. And so wouldn't you agree that its domain goes from 0 to infinity, and likewise its range goes from 0 to infinity? Okay. You know, you don't quite see the switching happening here, but it is happening behind the scenes. Okay. All right. So last thing we want to talk about then in this section are inverse functions and composites. So if a function truly is one-to-one, then f inverse of x is unique such that f inverse of f of x will equal x, and the opposite, f of f inverse of x will also equal x. So essentially, anytime you do a composition of functions with its inverse, with a function and its with a function and its inverse, it should equal x, but you have to do it both ways. So down below, they say, let's use a composition of functions to show that the f inverse of x that's being given here is correct. And so the only way to prove that these two functions, that f of x, or that f inverse of x is the true inverse of the given f of x, is to show that these two pieces. I need to show that f of f inverse of x equals x, and I need to show that f inverse of f of x also equals x. So just like when we did the composition of functions before, work from the inside out. So over here on the left, f inverse of x, that's given to me. That's 4x minus 5. Now this says go to your f function. Everywhere you see an x, plug in 4x minus 5. So I'm going to my f function. I have 4x minus 5, and then I have a plus 5 up top, all divided by 4. Just start cleaning up. What happens to those 5's? Hopefully you agree. They cancel out. That leaves me with 4x divided by 4. And sure enough, then those 4's cancel out. And so that equals x. So we have shown that f of f inverse of x equals x. So we've shown half of it. Got to go the other way. So now over here, f inverse, work from the inside out. So f of x we know is x plus 5 all over 4. This says now go to your inverse function. Everywhere you see an x, plug in this x plus 5 over 4. So I have 4 parentheses, x plus 5 over 4 minus 5. Notice now, think of this as like 4 over 1. What would happen to these 4's? Cancel out, right? That leaves me with x plus 5 minus 5. What happens now to your 5's? They also cancel out. And now you've shown that f inverse of f of x also equals x. You have to show both to indicate that it is a true composition of functions and that they are true inverses of one another. Okay? And I'll let you try example 9, and you can check yourself with the solution key. Let me know if you need anything. Thanks a lot. Bye.